you. I welcome the opportunity to speak to you here today. I'm going to talk about the sustainability of outer space and sustainability in terms of the physical sustainability. So physical objects in space, space debris. I'm going to talk about our frequency spectrum or space weather, because those are different issues from sustainability. You're probably all aware we're reaching 60 years now of outer space operations with the anniversary of the Sputnik launch yesterday. Since then, we've had about 8,000 objects, and this is not going to work. Okay, I have a little video, but anyway, it just showed how over the past 60 years, the number of objects in outer space had grown. It's a little video. So space debris, you're probably all familiar with, but what it actually consists of. And inactive satellites, of the 8,000 satellites that were ever launched, a lot of those satellites remain in orbit, even though they've been inactive and don't work. We're at about maybe 2,000 active satellites at the moment. To give you an example, Vanguard 1, launched in 1958, was the 4th satellite ever launched into space after Sputnik 1 and 2 and Explorer 1. It's still in orbit, and it will remain so for at least another 200 years. Rocket bodies and upper stages. Usually the last stage of a rocket stays in orbit with the satellite. A lot of satellites don't have their own propulsion, so they need the last stage of the rocket that gets into orbit to release a satellite actually remains in a fairly similar orbit to the satellite that it releases. So there's a lot of empty pieces of rockets up there. But by far the biggest number of pieces are fragmentation pieces. That comes essentially, it is what it is, explosions of either rocket bodies, because if they don't expend all their fuel, they're prone to overheating over time, expansion and explosions. Satellites themselves have exploded, either from fuel and fuel tanks overheating, batteries overheating, or other sorts of malfunctions. And then we have some anti-satellite tests that have caused a lot of fragmentation. The biggest one was in 2007 by China, and I'll show you an example of that. And then, fortunately, we've had very few. There's been a few accidental collisions of satellites, orbits crossing, and the most famous one is the Iridium Cosmos 2251 in 2009, generated over about 2,000 pieces of debris. Overall, there's an estimated 7,500 tons of material in Earth orbit, and most of that cannot be maneuvered or controlled. And a lot of that will remain in orbit for a long, long time. Now, we've seen, if you've looked up space debris or looked up our videos, we've seen a lot of representation. This is an example that you can find on the internet. It actually gives you an inaccurate view of the space debris problem, because it projects the debris to be much, much larger than what it actually is in real time. There is a lot of space in outer space. So there, some of those dots represent debris which might be this big, and they're represented as being tens or hundreds of kilometers in size when you look at that. So it's a problem, but it's not exactly as represented. Well, where's all this stuff? Now, space is not it's not homogeneous in terms of where the debris is located. Obviously, the debris will be located mostly in the orbits where satellites have been used and where they've been popular. So generally, we have low Earth orbit, which is very useful for Earth observation, some communication systems. We've heard a lot about the ISS, the International Space Station, from the CISAT and science missions. The space station is at 400 kilometers, which is fairly low. A lot of the Earth observation missions are anywhere from 600 to 800 kilometers in altitude. The majority of the space debris problem is located in those areas. Medium Earth orbit is where we find all the GNSS, the Global Navigation Satellite Systems, GPS from the US, Day 2 from China, GLONASS from Russia, and Galileo from Europe. All of those satellites are in 12-hour orbits, about close to 20,000 kilometers from the Earth. There's not a huge problem in that area because there's relatively few satellites and it's a very large area. Geostationary orbit is a very particular orbit. It's located at 35,860 kilometers or so from the Earth at the equator. And it's very useful because at that altitude, it takes 24 hours for satellite to go around the Earth. And that corresponds with the rotation of the Earth. So useful for communication satellites. So if you have any antenna on the ground, you don't have to track a satellite, you point at one spot. Because the orbital period of a satellite is related to its distance from the Earth, that's the only spot where that happens. So you tend to have, you imagine a belt around the geostationary, around the equator at that altitude. So there's a lot of satellites there. Debris is a bit of an issue, but not too much because that's fairly well regulated and controlled. So just to give you an idea of densities at different orbits, you see the peaks at around 800 kilometers. Those are multi-year observation missions, and also the Iridium constellation for communications. And there's another peak around 1,500 kilometers, global star communication satellites, and a lot of former Soviet Union communication satellites were in that area. However, the densities are still very, very low. However, the problem continues to grow. So this chart shows the growth ever since the launch of the space age. These are the objects that are tracked by the Space Surveillance Network of the US. In brown, you see the total number of objects. The pink is the fragmentation debris. So you see that the fragmentation debris is the majority of the problem. You'll see some interesting discontinuities here. So in 2007, the China ASAT test contributed about 3,000 pieces of debris. You see that jump there. You've also heard in the following year, the US conducted an intercept of its satellite as well in 2008. USA 193 was a military spy satellite that had failed early on in its mission and was gradually degrading and was going to re-enter the Earth atmosphere. US said it posed a danger to the public, so they tested a missile and they hit it, causing a large number of pieces so that all the small pieces would then burn up in the atmosphere. They conducted that test at about 200 kilometers altitude, so that's why it didn't generate a lot of debris in the pieces immediately or within the next few weeks re-enter the Earth's atmosphere. And then the Iridium Cosmos collision in 2009 caused another jump. So we see by this trend, the number of satellites, the number of objects and debris continues to increase. Now these are just the numbers that we're up to closing in on 20,000 now. These are the number of objects that are being tracked and cataloged by the Space Surveillance Network. So they say they can see in LEO, lower orbit, objects about 10 centimeters in diameter. So we're talking 4 inches. We don't know how many objects are smaller than that. Estimates are up to perhaps 500,000 or more smaller objects that are just not trackable with current technology. This shows the few diagrams of the Chinese ASAT test. The first one shows the demonstration of the intercept. You see the satellite, which was a Fengyang 1C, an inactive weather satellite in China. They launched a missile. It intercepted it at 860 kilometers. It's like basically hitting a bullet with a bullet. Impressive in one sense, but unimpressive in another sense is that it generated over 3,000 pieces of debris, and most of which will be orbiting the Earth for over 100 years. And when you intercept a satellite, or when a satellite explodes or has a problem, it's not like an airplane that immediately comes down to the ground. It continues orbiting the Earth. And we see the debris, the cloud on the bottom picture, spreads out over the Earth, so it remains in sort of a ring like that. And because of conservation of momentum, all the pieces just keep going and just spread out over time. They will degrade over time because there's a slight atmosphere at that altitude, but they will degrade at different rates based on their geometry and their mass. And again, a few words about the Iridium Cosmos collision in 2009, the second largest debris event, and again, about 800 kilometers. Interesting about this one is that Iridium was warned that this was a potential collision. But Iridium gets warned every week about potential collisions, and the odds are very, very low. But eventually, if you go to the well enough times, something happens. So this generated a lot of debris. A lot of it will still remain in orbit for a long time. And this shows an example of the two debris clouds, one from the Iridium satellite, one from the Cosmos satellite. And again, you can see the orbital planes that they were in, and the debris spreads out over time. But it's not just the big collisions we need to be concerned about. We have various small pieces which will hit satellites, will hit the space station and cause minor damage. So this is an example. This is the actual photo from the Sentinel-1 satellite, which is a radar satellite for the European Space Agency. And they had installed cameras on their satellite to monitor the deployment of their solar panels and their radar array on the bottom. So when on the 23rd of August, they noticed a decrease in solar power, and they noticed the disturbance in the attitude of the satellite. And then the camera actually showed an area that the solar panel that was damaged. And this was calculated to be hit by a very, very, very small, a few millimeters piece of debris, which had been untracked, of course, because we can't track. So that was just the conclusion. So there are hundreds of thousands of these little pieces of untracked debris which cause problems. And when you're a satellite operator, sometimes you have problems with your satellite, you don't always know the cause. So there have been many cases of satellites malfunctioning with unknown causes. There might be electrical problems, there might be some type of other failure on the satellite. They may also be caused by some debris, and there's no way of knowing for sure. So how long do objects stay in orbit? Well, it all depends. The Earth's atmosphere gradually reduces in density. So when you're in the 400 or 500 kilometer range, there's a fair amount of atmosphere. And therefore, this chart shows, for example, the blue is sort of an average, what we consider to be an average deorbit time. And then with the red and the green, minimum and maximum lifetimes. The lifetimes are very hard to predict because the atmosphere up in those regions changes over time. It changes with solar activity. There's about an 11-year cycle of solar activity which causes the atmosphere to expand a little bit at those altitudes. It also depends on the size, ballistic coefficient of the object, which is its drag related to its mass. But generally, under 400 kilometers, objects will degrade if they're unpowered within several months. At about 600 kilometers, this chart there shows about 10,000 days. That's 27 years, to give you an example. So at 700 kilometers, we're 80 years, and above that, we're 100 plus years. A lot of our observation satellites are 600 to 800 kilometers. We have a lot of objects above that if they're left on their own, will stay in orbit for 100 or more years. You may have heard about the Kessler syndrome. Now, Kessler was a NASA scientist who advanced the theory that at some point, if there's enough objects in orbit, that collisions will become a self-sustaining chain reaction. Because once you cause some debris, other debris will hit other pieces, and they will break up. It's almost like a fission reaction. So the theory seems to be sound. The problem is no one knows at what density level this thing begins. There's just way too many unknowns. The consensus is we're likely still far, far away from this type of threshold. But the disturbing thing is that we won't know when we're near the threshold until it's perhaps too late. So just a word of caution. Not to be too scared, but just a word of caution. So who keeps track of that? I referred earlier to the Space Surveillance Network, and that's run by US Stratcom, UG Command. They have an extensive network of tracking stations, both radar and optical sites. So other nations contribute. For example, Canada, the Department of National Defense, has a satellite called Sapphire, which is in orbit, and it's used to take images of the geostationary belt and get updates on the location of geostationary satellites. The Space Surveillance Network overall can track objects as small as 10 centimeters in low Earth orbit. That's using their radars. Russia and China have national systems as well. We don't get much data from them. Hopefully in the future there will be increased cooperation. But France and Germany also have some good capability, and they cooperate with the US. One of the major detection mechanisms for the US is called a space fence. They had a fence in the central US, which is a VHF radar, VHF signal going up, and they would record the reflection of any object that passed over that. And using Doppler, they would track and catalog the objects. They're building a new one. And that new one is going to be located in the Pacific, Kwajalein Island, one of their test ranges. But because of the new technology, the higher frequencies they're using, they're going to go from being able to detect objects of 10 centimeters to objects of between 1 and 2 centimeters. So the estimate is they'll discover close to maybe 200,000 more objects in space. This will, of course, bring technical challenge of how do we keep track of that, because if you imagine StratCom now, every day cataloging 20,000 objects, running simulations as to where there might be conjunctions, where these objects are going to intersect the orbits of active satellites and provide warnings. That's already a huge task. So imagine making that task 10 times more difficult. But the other thing is that for the law students here, it's sort of a legal question. All the objects that are currently being cataloged are traced back to a launch, and the launching states retain responsibility for those objects, even the debris that come from their original satellites, all component parts. These will be 20,000 orphan objects. So those objects cause damage to other satellites or cause damage on the ground. There is no one to blame for it. If anyone wants to do some research on that, Law Institute dig into it. This is just a map of, again, showing graphically the space surveillance network of the US. You see the Canadian satellite on your top left, the Sapphire. The blue squares are radars, large radars that were built mostly for ballistic missile defense, but they are ideal for tracking lower orbit satellites. And the yellow dots located mostly around the equator are the optical sites that track the geostationary satellites. Commercial space tracking, AGI, Analytical Graphics, the developers of STK, which is a modeling tool software for space and missile applications, has established a commercial, about 10 years ago, a center for space tracking satellites for commercial companies. They use some commercial sensors. That's growing in popularity. It's growing in more companies are collaborating, and hopefully in the long run we see commercial space tracking and providing service to commercial companies growing. And so we can't just all leave it to the US military to do everything. So predicting collisions is a very, very difficult task. First of all, the sensor measurements have an uncertainty. Whenever you measure with radar, whether you measure optically, there's always a measure of uncertainty and how accurate you can be. But also, even more difficult is the propagation models. You measure, and then you have to model the flight of, or not the flight, the orbit of those satellites forward. And that's very difficult in space because you don't have very good measurements of the atmospheric drag at those heights. You have models, but they change a lot. And also the Earth's gravitational field is not 100% known. The Earth is actually quite lumpy. So there are areas where the gravity is slightly higher due to land mass distribution. For example, in over the Himalayan plateau and over the Andes, slightly more force of gravity over those areas. So there's a lot of uncertainty. So all they can do is predict when the conjunctions will be close and do these ellipsoids. So for example, this is showing perhaps a conjunction of two objects. So we know one is going to be somewhere in the yellow ellipse and the other one's going to be in the red ellipse. Whether they're actually going to meet at the same spot at the same time is a question of probabilities. And so the warnings are issued when these probabilities exceed a certain threshold, such as 1 in 10,000 chance of actually a conjunction, and then satellite operators decide whether they're going to make a maneuver or not. So I think in NASA, the ISS, they're probably a bit more careful than if you're an operator of a commercial satellite, because you don't want anything, the consequences of something big hitting the ISS with astronauts on board are much more serious than perhaps you're losing one Iridium satellite out of your 66 constellation. Anyway, it's a very difficult task. Measures to mitigate debris. Well, there have been measures since 1989. The U.S. Produced an initial report on how we can reduce that. NASA instigated the founding of an international group called IADC, the Interagency Space Debris Committee, and other agencies have joined. We're now up to 14 agencies, and they came up with debris mitigation guidelines. And then that was adopted by the UN. Unfortunately, those are guidelines. They're non-binding, they're voluntary measures. And these are governed by national governments, which license their own space operations. Some of them will say, okay, if you want a license to launch your satellite or operate your satellite, you'll have to follow these debris guidelines. Other nations don't. It's non-binding. It's one of the issues. So what did they say? The main things we need to remember, I guess, is the post-mission disposal. For geostationary orbits, the guidelines say at the end of your mission, you have to preserve enough fuel to raise your orbit by over 200 kilometers. That way it'll stay out of the way for hundreds of years. And for the lower orbits, you have to make sure that after your mission, that it deorbits within 25 years. It's a good idea. Active debris removal, you've probably heard about that. Can we go up and remove the debris? So there's a lot of concepts to try and do that. You can go and send a mission to grapple it and deorbit it. You can shoot it with a net, and don't laugh. It's actually seriously being considered by the European Space Agency to catch one of their big satellites with a net and bring it down. You can have these packs where if your satellite becomes disabled, it'll deploy some type of drag-inducing measure there that shows a balloon to deorbit it. And there's even studies using a laser to cause ablation on the satellite. Ablation is where material will move. The laser heat will cause the material to gas out from the surface and then sort of evaporate, and by the gas molecules exiting the satellite will provide an impulse and slow the satellite down. These are all research methods, but basically none of them are really provide a technical solution. They might be useful once or in a particular case. However, all of these methods are very, very expensive. And so if you want to remove debris, you need firstly to prevent having so much debris. And the last thing I want to mention, last thing I want to mention is what's coming up in the future. So there are proposals now for what's called Mega-Constellations. OneWeb just received a FCC license for a 720 satellite constellation. SpaceX, Boeing, Samsung all have proposals for constellations of thousands of satellites in lower orbit to provide internet, Wi-Fi type service. A total of, and if they all get their license, if they launch it, we're talking about a 1,000% increase. That's another title. 1,000% increase in the number of active satellites over the next decade. This has to be carefully managed. So at the end of the day, the outlook is uncertain. If we continue on the same path, eventually we won't be able to sustainably operate in space. It may not be now, it may not be 20 years, it may be 50 years, I don't know, but the trend is clear. Space is not self-cleaning. It's only self-cleaning in the very low orbits. Debris removal technically is not an option at the moment, maybe in the future. So we need to be warned that if we don't start thinking about improved measures, and it would be standardized international measures, not just leave it to individual countries, we risk at some point in the future that our grandchildren and our great-grandchildren will not be able to benefit from space the way that we are. And that was my message for today. Thank you very much.